Hi, everybody. I'm Val Wolf. I'm one of the executive directors at the Hamilton Clinic of OCAL, the Occupational Health Clinics for Ontario Workers. Very happy to welcome you here today. I think it's our 6th or 7th episode of our OC-COVID webinar series. And today we're talking about airing it out, ventilation solutions and tools at a critical time. But before we begin, I wanted to take a moment to recognize that yesterday has now become March 11th, the National Day of Observance to commemorate the people who have lost their lives to COVID, and as well as the significant impact it's had on people's health and on people's lives. And so I'm actually proposing to do a minute of silence, maybe, if we could, to recognize, and particularly I will to recognize all the workers and essential workers who've been affected, as well as seniors and people of all ages. So let's just take a moment to remember that. Okay, thank you. So now I'm actually going to turn it over to our moderator, who is Dr. Kevin Hedges, an occupational hygienist in our Ottawa clinic. Are you ready to take it? And Kevin will introduce our 3 speakers. It's going to be a fantastic session this afternoon, and I think we're all going to learn a lot and have a lot to discuss. And
welcome, everyone. My name is Kevin Hedges. I'm an occupational hygienist with the Occupational Health Clinics for Ontario Workers. I'm based in the Ottawa Clinic, and I really feel honoured to be able to present the speakers to you. But before I do that, I just want to give an introduction to the session. So this is our ongoing COVID science solution and success stories, and this is really airing it out, talking about ventilation solutions and tools at a critical time, and it really is critical. And we're just welcoming back Dr. Siegel, who's we're happy that he's going to continue and provide more information. But if you think about, all the different barriers that we need to prevent COVID-19, there's not one silver bullet. They're all important. So this is just a famous kind of Swiss cheese model, just to show it. And also the way Japan has managed prevention using the 3 C's. I thought that was pretty useful caption to put up as well. There's a very busy slide here, but I did come across a paper recently published on the 10th of March, and this is from the British Medical Journal. It does really talk about the increased risk from the new variant of concern with a mortality hazard ratio of 1.64, and which represents an increase in deaths from 2.5 to 4.1 per 1,000 detected cases. And in the conclusion in the paper, it says that the probability that the risk of mortality is increased by infection with VOC 2020-21 is high. So really, we're in a critical period now. And I just got this caption off of the article this morning just to talk about, the current situation. Sudbury in lockdown with grey, and this is also from the science table from the University of Toronto, and you'll see that the right on the right hand corner there, the SARS-CoV-2, it seems to be going down, but on the left, if you think about variant of concern, it's going up. So you know, all predictions are saying that we're going to be in a kind of a precarious situation. So then if I can just introduce our speakers. So we've got Dr. Lingzhu Wang from Concordia University. So Dr. Wang joined Concordia in August 2010, has been the Concordia University Research Chair in Building Airflow and Thermal Management. He earned a PhD degree in mechanical engineering at the School of Mechanical Engineering, Purdue University, Westlake, Fayette, Indiana, USA, 2007. Our second speaker is Thomas Smith from FreeFlow. I found out about Thomas through a webinar that he co-presented alongside of Lisa Brossu, and it was a really fabulous webinar. And you can actually see that webinar online if you go to the FreeFlow site. So he's the president of FreeFlow. He's worked for a long time providing safe, efficient, sustainable performance of labs and critical workplaces. He has a Bachelor of Science in Mechanical Engineering from North Carolina State University and a Master of Science in Industrial Hygiene. What a great combination, from the University of North Carolina. He's served on numerous committees for development of national and international standards on ventilation for safety and health, and he serves on the board for the International Institute of Sustainable Labs and is a member of the Alumni Hall of Fame for the Mechanical and Aerospace Engineering Department at North Carolina State University. And I just want to welcome back Dr. Jeffrey Siegel. Jeffrey Siegel is a professor of civil and mineral engineering at the University of Toronto and a member of the university's Building Engineering Research Group. He is internationally recognized for his work on indoor air quality generally and air cleaning specifically, and is also a fellow of Ashrae and a member of the Academy of Fellows of the International Society for Indoor Air and Climate. He has published over 100 peer-reviewed articles on indoor air quality and related subjects, and has been active in disseminating information about filtration and ventilation solutions for COVID-19. I'd also like to introduce you all to Dr. Sarah Adaman, who's an emergency doctor actually, but she's also on a coalition that a few of us belong on, looking at aerosol transmission. Sarah's also a concerned parent, and I thought it'd be appropriate to share Sarah's story before we get into the webinar.
Yes, well, first of all, thank you so much for having me. I never thought I would be participating in a webinar like this. So ventilation isn't something that I had given a lot of thought to. Like everyone else, though, I was obviously quite involved and engaged in the discussions all around the pandemic when it started. I work in the emergency department, so one of the main questions for me from the very beginning was around the transmission of COVID and how can we make ourselves safer in our workplaces and in all our indoor spaces. Initially I accepted the dogma at the time regarding contact and droplet transmission, and so the precautions in place seemed quite reasonable. And as I mentioned, didn't really think much about ventilation. And then I guess as the months went on, I think like many other people, we started hearing more and more about the possibility of aerosol transmission, even airborne transmission. And I just started reading more and listening to what experts outside of sort of my regular field were saying. And, over the summer, I read a lot of the pieces put out by Jose Jimenez and Zeynep Tufekci. Lindsay Marr, of course, was writing a lot about this. So I just started getting quite interested in it. And then it was around, I guess, July or August, and I was starting to think about my kids going back to school. And I realized that my children had not been inside any indoor space since March. So I'd been going to work every day, but my husband was working from home. My kids had not been anywhere except within our own home. And at the same time, there was more and more coming out about the importance of good ventilation. And so that led me to wonder what the ventilation is really like in my children's school, and to realize that I had no idea. So I then started talking to other parents at my children's school, and sort of there were a number of us that were wondering the same thing. And we were hearing that ventilation is really important. And we were eagerly awaiting some guidelines from the ministry or from the school boards regarding, ventilation. And instead, what we saw was a lot of information about the safety measures that they were going to take with regards to preventing, droplet and contact transmission. So there was a lot in the opening, the guidelines on reopening from our school board about cleaning surfaces, about sanitizing the kids' hands, about quarantining the library books that the kids borrow, this kind of thing. And there was essentially nothing about the quality of the air and how they were going to put in place safety measures to prevent transmission of COVID through the air. Sure. Well, I suppose I was a little bit naive because as soon as I started reading about how important ventilation was and how one way to mitigate inadequate ventilation is with the use of portable HEPA filters or air purifiers, I figured that it would be a no-brainer and that the school would be fully on board. But I obviously don't understand how bureaucracies work. So a group of parents and I, along with a group of parents, we emailed the principal. We proposed that donating purifiers. We weren't asking for any money. We said we actually had already bought 4 purifiers amongst ourselves. We'd done the research. We know they were a decent size for the rooms in the school. And we got back an email that just said, no, I'm sorry, we can't do that. And so I was pretty shocked at first. And I started doing more research about the benefits of air purifiers outside of just preventing COVID transmission. So there have been, some studies showing benefits with regards to cognitive functioning and concentration. So, sent those back again and still sort of kept getting blocked essentially by both the school and really by the school board. And I realized with these things that it's sort of the directions come from above. And so everyone is just doing what the organization or person above them is advising. So our principal, the safety measures that she had put in place were those that had been recommended by the school board. The school board felt that they were following the recommendations made by our local public health unit. And I assume our local public health unit was following those of the provincial and so forth. So I realized that it was really a problem sort of going many layers up. And my principal was really just trying to do the right thing and follow the guidelines that she had been given. And she had not received any information about the importance of clean air. So we then, as we had to advocate at a sort of a higher level, and we started attending the school board meetings, I contacted the trustee for our school board and started having conversations with her and sending lots of articles and information about the importance of, aerosol transmission of COVID. And made a few allies that way, probably a few enemies as well. And then we presented again I attended several of the school board meetings. And essentially what we realized is that the first step was to have an actual assessment of the ventilation in our buildings. This ended up not really being a true assessment. It was more just the school board looking at all of the schools in the board and determining what kind of ventilation they had. So you'd think this information would be very readily available, but apparently it wasn't. So then they sent us back a response explaining that, yes, in fact, our school did not have mechanical ventilation, which we all already knew. And there were a couple other schools within the board that did not have mechanical ventilation. And then this was followed up by the board agreeing to provide purifiers for the schools that do not have mechanical ventilation. So we were really excited when we got word that they were going to get the air purifiers. We, of course, had been trying for months at that point just to donate our air purifiers that were sitting in, I had a few sitting in my living room, quite large ones. And so eventually they agreed to let us donate ours while they were waiting for theirs to arrive because, as you probably know, a lot of other people developed an interest in ventilation during that period as well. And so we first started advocating in August. By the time we convinced them that it was a good thing to do and to purchase these filters, it was at that point already either I think late September probably. And of course, there was about a 6 to 8 week wait for any of them to arrive. So they agreed to accept our loaners, and then eventually sometime around, I think probably late November, early December, we finally got purifiers for all of the rooms in the school. So the situation, we have been quite fortunate in our school. There weren't any cases actually in the fall that we know of. There was a case recently amongst in our school, and as far as I know, there has been no transmission. I think it's really careful. I don't want to make the leap and give the air purifiers all the credit for preventing transmission within the school. As I said, there's only been one case that we know of, and there are a lot of, as everybody knows, with regards to transmission of COVID, there's a lot of luck and a lot of other factors involved. So, did it play a role, the air purifier? Maybe. I can't say for sure. I'm certainly happy that it was in place. I'm also happy that as of January or early February, when the students went back to class, there was a mask mandate in place for all the students starting at grade 1. Prior to that, it had only been at grade 4. So I think all of these things make a difference. I think that the air purifiers are, one layer of protection, and you obviously have to continue to support all the other layers as well. Well, I was just going to mention that we didn't actually stop there. We then started advocating that they assess the ventilation with CO2 monitoring. So they have conducted that research as well, or that study. So the measurements were all taken before Christmas in the classrooms, so which is fantastic. Unfortunately, I'm still waiting for those results, so we've not seen the official report yet. In the meantime, I have sent a CO2 monitor in with both of my children into their classes, and the results have been concerning, I would say. So we're continuing to advocate on that, and it's clear that the air purifiers are necessary given the levels of CO2 that we are seeing in the classrooms. But I think that you can't just stop there. And so we're continuing to pursue this and to advocate for, a proper assessment of the ventilation in our school, and then more mitigation measures as well to improve it.
That sounds like a great measure, actually, measuring carbon dioxide. If the levels are high, then what that tells me, it's really important that air purifiers are put in the school. And, in the longer term, more fresh air is provided along with mechanical ventilation.
Exactly. Yeah. So we've been advocating since the fall for the windows being open. And that is something that the school was advised by our public health unit, was to keep the windows open as much as possible and the doors to the hallways. The problem is that we live in Canada in the winter. And so I don't think that the windows have been open as much as we would like, just for reasons of, cold weather, obviously.
Do you know if the school actually looked at mechanical ventilation, or is that something that's in the process? Is something that's happening at the moment?
I don't think so. It's a very old building, and our school is actually just renting this building right now. It's supposed to be temporary. We're supposed to be getting a new school. Of course, it seems to be taking longer than expected. But I don't think that they are looking into changing the whole ventilation system and installing mechanical ventilation in the school. But I could be wrong. It would be great if I was.
Okay, I just want to thank Sarah. So that's a recording. Sarah wasn't available. So Sarah's been a stalwart as part of the coalition I belong to, to really talk about the importance of aerosol generation of COVID So I just want to now hand you over. So the way that we've actually organised this webinar, we want to sort of start off at a very high level. We want to look at, the risk for cities and buildings in cities. And then we want to look at buildings, and then we really want to drill right down and look at air purifiers. So that's why we've ordered it this way. And the first presenter that I want to give you is Dr. Wang. So I just really want to thank you for offering to present, Dr. Wang. Over to you.
Okay. Thank you, Kevin. Hi, everyone. So my name is Liang Wang. I'm Associate Professor at Concordia from the Center for Zero Energy Building Studies. And today I'm going to report some recent work on evaluating, monitoring, and mitigating of SARS-CoV-2 airborne transmissions at an urban scale and inside buildings. So there's a few topics, and the focus will be about this new website we created for evaluating the infection risk and mitigation strategy for buildings. It's called the CDR-PI. And I think before I start, I think I would like to share some of my experience with how this get me started. So similar to Sarah's story, I'm a concerned parent. Last year when this whole thing started, I'm concerned about my daughter's school and the risk, and also my younger daughter's daycare. And the first thing what I did is I think that's in January last year, I built a UVC system myself for my family. And then later, of course, I bought an air cleaner also. And then later I was contacted by a few colleagues in the States, and they asked me to do some work for them, and mostly about modeling and evaluating the risk. Then I found out I can be more of a use for during COVID, and that's how this started. Right. So as some introduction, as Kevin mentioned, I got my PhD from Purdue in 2007 from mechanical engineering. After that, I worked as a postdoc at the NIST, working on developing multi-zone airflow and air quality models called CONTAM. And lately, we have collaborative project with them, develop models to model COVID, and this new model called Fatima. And also, I have been working in the past on gasoline power generators, and that's my experience on that. Then talk about the COVID, and as the Val mentioned, it's almost over a year was recognized, COVID-19 recognized a global pandemic. And it was not until recognized airborne transmission of major routes until the early October last year. So airborne transmission is one of the a few major transmission ways. When the infected person speaks and talks and sneezes, the very loaded particles can travel in a far distance driven by the air flow. Depending on the building ventilation system, as Sarah mentioned, you may have mechanical ventilation or natural ventilation by only open the window. There are different strategies to mitigate the risk level. And as we all know, wearing a mask is considered the most effective measures, and staying less time in the buildings and reduce number of people in the space will also help. And top of ventilation, increase the outdoor ventilation rates through your mechanical system or by opening the window will also help to dilute the burst load in the space. If you have mechanical system, upgrade your filter in the ductwork like MERV 13 can also help. And lastly, but not least, to use portable air cleaners will be also a strategy. So I think the one of first important thing is critical is to quantify the airborne infection risk. So there's a well-known model by using called the Welsh Valley model. The concept of this model is to, in the terms of quanta, we have a one quanta of COVID-19. That's calculated what is the chance to get infected will be around 63%. As you can see from this equation. So the quanta numbers inhaled by the person is a function of the concentration in the air, that's the C average, and your exposure time. The longer you stay, the higher risk, and also the number of people in the space, percentage wearing a mask, the mask efficiency, and etc. So the first concept to evaluate the risk is called individual risk or conditional probability of infection. So what it does means is if you have an infected person in the space, in the room, as you in the same room, the chance you can get infected. So it's called individual probability of infection. In comparison, another concept called building or community level of infection. So this is a function, the risk is a function of the prevalence rate of in the region or city. And so if you're not sure if there's a person infected in the space or not, the probability of infection of the person in the room depend on the local prevalence rates. And the more people in the space, you're going to have higher probability of infected person in the space. So that's why we call the building level infection risk. So put another, in other words, 1 minus this probability called PB means at the end of the day, the chance of all people can survive. Or in other words, another way to understand this risk is called at the end of the day, for one particular building, what is the chance for at least one person can get infected? So in the study we are working on is we are using both risk evaluations. So as I mentioned, we are creating this new website that's called CDR-PI, and one of the major motivation is to fight against COVID. It's not one person or group person's efforts. It should be a collective efforts of the public, and so then we can act together. And if some people do not follow the prescribed rules, that will be a problem. So we need to work together and to fight against the spreading in the public. But the problem is the public should have the knowledge and the information or the suitable tools to evaluate the risk, and they should be well informed. There's the technologies in terms of ventilation and mitigation that they can apply in their buildings. So that's the purpose of the creation of websites, to disseminate the knowledge of ventilation, infection risk, and different mitigation strategies as a function of local prevalence rate, occupancy, and different scenarios. So this is the website. If you can search, I think we can also provide a link, the front page. I also have the website opened up. You can see my screen, right? So this website.
Yes.
So the first thing you will see, the front page is a disclaimer, and then you click here, getting in. The first thing we'll look at is the whole North America, USA, and Canada map. And the color shows, red color shows higher risk of infection for airborne transmission. And all these rates are calculated based on the daily prevalence rate for a city. And you can move your mouse around. See, right now for the apartment type of building, I think it's around the Missouri in the States. If you go to Canada, you can also check Quebec. So right now for this region, the current risk, this risk is in terms of building risk is less than 1.1%. The total cases so far is all close to 9,000. And then you also can select different type of building. For example, for assembly building, where we have more people's occupancies and probably fewer poorly ventilated space, then you can have a higher risk. And then at this drop down box, you can select different strategies, so you can get a overall idea of how effective different strategy can be. So wear a mask, how effective compared to the baseline case, no mask, and then you have reduced staying time, filtering, MERV 13, and on relative scale, and also your ventilation rates. So this is the one user interface. Another user interface is on the city scale. I click the Montreal. On the left-hand side, you can see a drop-down list where you can see the current prevalence rate and new cases in the order in descending way. For example, in Canada, as of today, I think that's believed as today, the most the province, the most new cases in Ontario. It's about 1371 cases. But compare among all provinces, Saskatchewan is with the highest prevalence rate, about 0.53%. And also you can also compare for the USA, the city with the most new cases in New York City. So it's over 7,000. So this database is updated daily using New York Post database. And on the urban scale, and you can move your mouse around to check for the building of interest, there's a list of strategies you can evaluate and compare. On the right-hand side, there's a list of building types. You can hide or unhide buildings. Here, if you click apartment, that shows these apartments. They can go there away to check for apartment building, what will be the risk and the strategies. So also here, I just provide a link for show schools, which is of the, I think one of the major concern. And then, you can also check strategies on the city scale, 50% or 100% occupancy and ventilation and etc. It shows the color shows how effective the different strategies. Well, on the other hand, if you are a building owner or your engineer or manager of building, you know more details about your building. For example, you know the size of your space, the number of people in the space, and your ventilation system, air turn rate, etc. And then you can go click for, you can search your building, you go to your building and click over here, provide your information for your own building. You can do a more detailed analysis. And then also different city or province or country have different lockdown dates. You can also provide the lockdown schedule for your city. And if you click to the next, then you give you all period risk level in terms of the building risk, last month, last 7 days. And then there's ways you can evaluate the risk level versus outdoor air ventilation rates with or the mask, without mask. At the bottom is a comparison for different MERV ratings, 8, 9, 10. Each MERV rating provide a different efficiency of filtering viruses, 20% for MERV 8, 16, 95%. Then on this side, you can also select if you would like to choose the air purifier cleaner. You can choose the this is capacity called CADR, clean air delivery rate. You can see how effective and for different capacity of air cleaners. There's another tab called air cleaner calculator, where we have this calculator was based on the Harvard CEU Boulder portable air cleaner calculator from them. And basically, if you want to size your air cleaner for a space, you can provide information here. And then there's a scale. You can evaluate what will be the acceptable ventilation condition: good, excellent, low, barely, minimum, or ideal. So in this case, 4 to 5 air turn rate is considered by this calculator as good ventilation conditions. So that's the website. So if you have a chance, take a look. And if you have any comments, we are still improving the website, and please send along.
Thanks very much, Dr. Wang.
Let me see, let me hide this. Oh, I hide this.
You've still got more slides, sorry.
Oh, I also hide, yes, right. Now, yeah, I'm back to slide. So we know how to evaluate the risk. Then the next thing is, what is the current situation, right? So monitoring the ventilation condition and relate ventilation condition to risk is also important. So I think Sarah mentioned about the importance of CO2 monitoring. And last year, nearly the end of last year, I think December, some Montreal school teachers, they measured the CO2 level in classroom secretly, and they have the data, but they don't know how to interpret the data. CO2 level. Some of the rooms, mechanical ventilation, the concentration can be close to 2,000 ppm. Some classrooms with natural ventilation, they can down to 1,000 or even higher concentration. So I was contacted by them and tried to help them to interpret the data and relate the CO2 level to ventilation conditions. So they provide the type of the building, ventilation system, volume, and occupancy schedule, and the number of students, and the age. because age is important because of this. Different ages have different CO2 generation rates. So as you can see from this result, so room 1 is with mechanical ventilation, and the CO2 level is found that is close to 1,000 maximum. That's the red line. For the room 2 and room 3 with natural ventilation, the room only have windows open. At the end of the day, the concentration level is close to 2,000. So by using a method called Bayesian calibration, it's a statistical method where you can evaluate the uncertainties and probabilities of different parameters. Then we can infer what would be the ventilation rate based on the CO2 measurements. And based on these methods, we are able to estimate for room 1 with mechanical ventilation that the air turn rate is about 2 air turn rate per hour. For the rooms 2 and 3, where the windows only opened, the ventilation rate is less than 0.5 air turn rate. So I think compared to the 4 ACH I mentioned previously, both of the rooms, all the 3 rooms, the ventilation is not good. I would say poorly ventilated, even with mechanical ventilation system. And to help the teacher who have a better idea for other cases, so we developed these charts. So what these charts tells us is how can we estimate from time average CO2 level. From that, in terms, we can get ventilation rates. For example, if the measurements for 1 day, measurements for 600 ppm, that corresponds to 4 air turn rate in the room. So really, if you want to achieve 4 air turn rate in the room, the CO2 level you are looking at for the daily average should be close to 600 ppm, which is pretty low, much lower than the province recommended value 1,000 ppm. The reason is because of the typical way of recommending CO2 level 1,000 or even higher. It's based on the previous IAQ work. Because of the highly infectious transmissibility of COVID, much lower CO2 level should be, we should monitor for much lower CO2 level in the classrooms. So a few important things to note. CO2 readings can be instantaneous. So if you have a breath on the meter, the CO2 level can fluctuate. And so it's very important to really, we need to look at the time average of the CO2 level instead of instantaneous one reading. And also air cleaners cannot remove CO2. So if you have air cleaners installed in the space, well, you still have a higher CO2 level. That does not mean your space is risky. So this morning I asked my daughter to send a picture because of in her classroom there's air cleaner. So so this air cleaner I was told this was placed near to the teacher in front of the class. I think since they have the air cleaner in the school, so far there's no new cases in this school. And this shows how can we relate. We call the CO2 threshold value for COVID-19 as a function of exposure time. For example, if for 6 to 7 hours exposure, to avoid community spreading, where we call R0 less than 1. R0 is a parameter called reproduction number. To avoid the spreading, this R0 should be less than 1. To avoid spreading, the really time average CO2 for 6 or 7 hours exposure, we're looking at 500 to 600 ppm for COVID, for the COVID period. And luckily, the Montreal School have realized the importance of CO2 monitoring, and they started collecting CO2 in over 400 schools since about 2 months ago. The data is still updating on their website, so we're helping them to analyze the data and probably using the same method we are proposing. And once we have risk evaluation models, we know what will be the existing conditions. And now the next thing is how can we mitigate the risk, particularly for public buildings, considering we're going to have probably reopening of the public buildings pretty soon. And in terms of public buildings, there are quite a few more strategies we can apply to protect or curb the spreading. And we have been working with collaborators and try to evaluate different strategies like MERV filters, outdoor air ventilation rates, following the Ashrae guidelines, air cleaners, UV lights, and the combination of all of them, and also looking at CO2 level monitoring, and also the percentage of the importance of wearing masks. So this is all the models we can evaluate. At this moment, we focus on medium office buildings, large office, small hotel, retail, and secondary schools. And all these models are available and based on the architect library developed by Department of Energy and this model they provided to us. So I show you a result over here. It's a new result we get from large office and try to evaluate combination of strategies. And so the y-axis is the individual risk level, as I mentioned previously. On the x-axis is different ventilation rates. The baseline is the Ashrae guideline. 1.3 means 30% more outdoor air, double outdoor air baseline, 100% outdoor air. And for each of the category, we have combination of these techniques, MERV filters, air cleaners in terms of capacity. And as you can see here, to achieve the goal of the risk below this line is the R0 V1. Then these colored meshed results bars are those when everyone in the office wearing masks. As you can see, even later we have reopening the public building like this size. And it's very important, we still need to enforce the rule of wearing mask for this. If you don't have wear mask, if you don't have enforce the mask wearing, even you have really large air cleaners, and then the risk can still be high. So it's very important to control the virus at the source by wearing masks. And there's a tons of more information will be available from this website called iaqresources.ca, from the Canadian Committee of Indoor Air Quality, where I'm also a member. So we are a group of independent experts or committees, including engineers, academics, practitioners, and academics, and scientists and public health. And we are designed a specialized module for COVID-19 in buildings, including technologies, guidelines, new information, studies on air cleaning, disinfection, and administration information. So recently we are updating, hopefully this week will be out, to study the new variants with 1.7 more transmissibility, and then the report will be available later at the website. So here it shows the one of the new we provided compared to the older variants and new variants, what will be the required minimum ventilation rate to reduce the spreading of the virus. And lastly, I would like to acknowledge the financial support partially by the NSERC Discovery Grants, and special thanks to my colleague in the States, Dr. Miller and Dr. John Jai from UC Boulder, and Dr. Michael Lacaze from NRC through Eureka Project, and a few others at NRC, and Dr. Mag Sears from CCIQ and other CCIQ members working so hard on this module, and colleagues at US NIST for helping with simulation, and of course my colleague at Center of Zero and Big Study at Concordia. And also I need to acknowledge the support and data provider of CO2 and all the contributors of collaborators of Montreal schools. So that's my presentation. Thank you very much.
Thank you very much, Dr. Wang. There's a great amount of information there, and it's great that we can now have a look at the tool and play around with it. And really, it's about risk communication, isn't it? What gets measured gets noticed. What gets noticed gets action. So it really helps us focus in on where the higher risks are. What we thought we'd do is maybe just pitch maybe a couple of questions at you. We see there's a question from Dorothy Wigmore in the chat box, and so it's to yourself, Dr. Wang. What criteria are you using for face covering efficiency in the program? And she said, have you accounted for the new ASTM standard? And we know that we're just talking about face barriers here, and there's issues around face fit which aren't really dealt with very well, but maybe the air is new. But I'm just wondering if you'd want to comment on that at all.
Yeah, so for the model on the website CRPI, we use 30% and 50% for inhalation and exhalation. And for the other study, I showed the whole building mechanical ventilation. That study, we use 50% for both efficiency per mask.
Thank you. So we also have a question from Sammy Tardif. What is the link between carbon dioxide levels and the risk of COVID-19 transmission? I'm sure you get a lot of questions like that. Maybe you can share an answer with the audience here.
So the idea of this is by using the measure CO2 level is change with the day and also change with the ambient condition, indoor, outdoor temperature, particularly also the student schedule in and out of the classroom, number of students. So we're able to back calculate, infer the ventilation rate in the space. And then with ventilation rates as inputs and as to the risk model, as I mentioned slide, then we can calculate because of the ventilation rate, a function of the concentration level, C. And then we have the CO2 level, ventilation rates, go to the concentration level, then we go to the risk level. So that's how this works.
Great, thank you. And we also have another question here from Jason Sadowski. What is your opinion of the effectiveness of UV and HVAC for COVID-19? And maybe one of the other speakers can address this further on down,
yeah.
You know, through the, but just with, can the residence time of the air in the unit be long enough to be effective? Maybe one of the other speakers might chime in too. You're welcome to.
Yeah, to talk about UV light, because you see here for this public building, we do the modeling, and then we some of building, for majority of building, we find UV light in the room, upper room is quite effective compared to the UV light in the duct. I don't know if that answers your question or not, but you have to be very careful about UV light because it generates other things, right? I mean, ozone and may have other problems. So, but in our analysis, UV light is pretty effective. I think we assume that UV light, the effective air turn rate, we use that for that.
Great, thank you. More from Dorothy Wigmore. Can you explain how the number of people in a space affects carbon dioxide? Does it not affect using specific numbers as cutoffs for carbon dioxide?
Yes, like I mentioned, definitely you have different situation. The result I showed we use only for classrooms where the students only have a pretty much lower CO2 level or generation rates. If you like try to consider a gym where people work out and adults, the generation rate of CO2 can be much higher, and then different strategies should be implemented. So the method we presented can be applied for different situation. So I'm just thinking like we're also working with colleagues in RC, and probably in the near future, CO2 will be similar to a thermostat and to be installed everywhere in public buildings to monitor air quality in the space. I think that's a good initiative to work on.
Thank you so much, Dr. Wang. And I know Sarah has already reached out to you with some questions about CO2 as a follow-up to what she's been doing as well. And I think it doesn't look like there's any more questions. And just on behalf of OK, I won't get a chance to say thank you at the end. We really appreciate you sharing this information with us and giving your time to us as well. So thanks for your time with us.
Thank you.
Next presenter is Tom Smith from 3Flow. And I think I'll just hand it over to Tom, and he can introduce himself again and then deliver his part of the webinar.
Thank you very much, Kevin. I really appreciate the opportunity here. I'm really honored to have the opportunity to talk with you today. This is a very important topic, and it's one that we're all in this together. No matter where you live in the world, these issues are relevant. And I really appreciate the opportunity from the Occupational Health Clinics of Ontario workers to have this opportunity today. It's a lot of work that goes into putting these on, and to be able to speak with Leon and Jeff is really a great honor for me. So I we've been working in laboratories, 3-flow, for over 25 years. And you know, in laboratories, they work with aerosolized and airborne hazards on purpose. And there's many tools and techniques to control exposure. But we're looking at now, not laboratories, but any space could be a potential area where there could be transmission. And so we can't make a general space into a laboratory. And so I thought, what can we draw from our experience in labs that could be useful for non-laboratory type spaces? We started looking at how do we look at some practical tools to really help people implement measures that would enable them to mitigate risk and use better utilization of resources, and not try things that may not work, but to really look at good solutions and effective reduction in transmission. So I start first with, what does success look like? And we have to get people back to work. We have to get kids back in schools. It's really important to our society to do that for all kinds of reasons. And of course, we want to make sure that those are safe places to work. And there's a lot of unknowns, and the research work that's going on is critically important. But there's been a general failure to recognize early on the potential for, and the significant potential for, aerosolized transmission. And as a result, some of the efforts have been misguided and have, in my opinion, have been a poor use of resources and a lot of money spent on things that just aren't effective. And so we want to look at how do we maximize the effectiveness of our efforts. And then, of course, as we're collecting information and learning more about our building and our HVAC systems, how do we use that not only for today, but how do we use that information to help us in the future? How can we operate buildings that are more effective, efficient, sustainable, and resilient in the event that we have issues in the future? So we want to manage risk to as low as reasonably achievable. That's the ALERA concept, very popular in industrial hygiene concepts. So as I mentioned, research labs are specially designed to protect people working with hazards. However, when we look at commercial HVAC systems, they're not. They're quite frankly not designed to protect people from aerosolized hazards. And so it's very well known now that poor ventilation imperils the lives of people. And so when we look into a space, how do we know the ventilation is okay? What can we do to evaluate the configuration and the operation of these systems to ensure that we have a mechanism to protect people? So if we look at the system and just kind of build up a system, we're going to start with the space. We add some people into that space, and we're going to call that the communal airspace because people are sharing that air. What is exhaled is being re-inhaled by someone else. And so we need to look at that. Now, we can add some ventilation systems, air supply and exhaust. That's going to provide air to the space and bring air out of that space. That's the ventilation component to it. And we need to also look at how much of that air is recirculated versus fresh air. And so we can start to look at these systems in terms of what's happening below the ceiling and what's happening above the ceiling. And our remediation measures should take this focus of what are we going to do below the ceiling, where the spread typically occurs, and how do we better equip the systems to provide an environment that's conducive to safety and efficiency. So we know that infections primarily occur in the communal airspace, where two people are sharing the same air. One may be infected and the other may be healthy. They're only healthy for as long as they can resist that infection. And so we start looking at what I call the cone of corona. So as people are exhaling, they're emitting particulate, which may be laden with the virus, and that may be potentially spread to other people in that space. And so when we look at the amount of material generated by an average person, it's quite significant, 40,000 particles every 15 minutes. And that's going to increase or decrease, as Leon was saying, depending on the activity, it can produce much more or less depending on what they're doing and their state of their health. And so we don't currently know the infectious dose for corona, so we have to go as low as we can. But the infectious dose is the concentration times the duration of exposure. And that's very important. We want to limit the concentration and the duration. So now, as we look at this thing, are you downwind? Are you in the path of this particular concentration? So looking at accumulation in a space, when someone walks into that space and they're exhaling particulate, potentially laden with the virus, then it begins to increase that space. And if it's a well-mixed space, it increases and continues to increase until the generation stops. Now it's going to reach some point of what we call a steady state concentration, but when that person leaves, then it begins to decay. And it's this area under the curve that's known as the dose. It's the time that you begin to be exposed till the time that person leaves and beyond when the room removes those particulates. So dilution and contaminant removal become very important. And all of the considerations are a function of this well-mixed space. But we don't know if that's a good assumption or not. And we have to look at the ventilation systems serve multiple different areas. There may be different requirements between a waiting room or a procedure room or offices or labs. They have different functional requirements and therefore may have different design and operational parameters that we have to include. So we can look at the question, what is good ventilation? What is good for one room? Is that adequate for another room? And what are the risk factors that might come into play if we're going to evaluate these different spaces? So as having, decades of experience working in laboratories, I operate a business. I have to have people come back to work. We have different types of spaces, from offices to conference rooms, break areas, and training center. So I need to be confident that I can bring people back into the space safely. And what are these risk factors? And so that led us to use some of our experience from labs, where we categorize labs in terms of the severity of the hazard, the quantity, how it's being generated, to quantify or create a risk banding process. So negligible might be a space where you have, no occupants or one occupant can't infect yourself. Now, as you move down the spectrum, you start including things like ventilation and the other administrative controls and how many occupants in close proximity, and these factors begin to become very important. And so you can now look at a way to categorize spaces as a function of their relative risk. So we look at a traditional ventilation investigation is to evaluate first, what is the risk? What's the demand for ventilation? Where are the spaces of concern? We want to then inspect and measure the operation of the HVAC systems. Then look at the airflow patterns within that space. Airflow patterns matter. And then finally, if we have to, we can go to a quantitative test to conduct some aerosol tracer studies to evaluate the effectiveness of the space and what is the benefit of adding mitigation strategies such as local air purification. So let's start first by looking at our risk assessment. So we take our floor plan. It's the first piece of information you need. Get your floor plan, and then on it, locate where people congregate. Where are the known occupants and how many people occupy the different spaces? Where are visitors coming in? How many visitors? It's a very simple analysis to do. That gives us one piece of the puzzle. Where are people congregating? Then we look at the layout and configuration of the system. We have supply diffusers and exhaust grills, and hopefully they're coupled in each room where you have a supply and exhaust, and hopefully we have ventilation. And we want to look at the types of units. Are they recirculating? Are they outside air? How is that operating to help us protect people? Now we take this information and put it into a spreadsheet. We developed a simple spreadsheet. It's public domain. You're welcome to it. Just send me an email. Information will be available here at the end. And if you like, you can input information about your space, the size and type, the operation, the information about your occupants, some HVAC information, and then it'll calculate the associated risk with that space. Now, it's not as sophisticated as Leon's model, of course, but we're trying to sort spaces first, identifying spaces of concern. So by having this kind of categorization and a list, we can identify spaces and differentiate those spaces by their level of risk. And as turns out, in my office space here, we have 28 spaces, and only 5 are going to require some special measures. So we're now targeting the areas of concern. Putting this on our color code, we've color coded the floor plan, very simple, easy to do, and we identify the spaces that we have to take some more action. And so in our case, the training center is very important to what we do. We always want to enhance the knowledge base of people and have them go out there and implement solutions that work. And so training center, we need to bring people back. And so that's an area that we're going to focus on as our highest area. So we need to move to the next part, which is inspection of the operation. So now we get a layout of the system that's serving our training center. And the blue is supply and the red is exhaust. And so we can see that we've got a network of supply going out to the space and we have exhaust returning. But we need to know what the air change rate is. So we have to then do some measurements, and we look at the measurement of these values. You can get a local test and air balance company or your HVAC contractor, do these measurements. They're quite simple, and then do some correlation and calculations. And we turned out that we're able to calculate the air change rate. But I have a question here because we calculated 4.6 air changes per hour. It sounds like a lot, but this air is recirculating. It's going from this space back to the air handler and then back to the space. So it has a potential to potentially recirculate contaminants back into the zone. So how much of this is outside air or fresh air? We need to make that distinction. So we're going to evaluate that a little bit further. Okay, we've got the air change rates, but what do we know about the airflow patterns in that space? So looking at some airflow visualization tests, a very simple tool, generate a little bit of smoke, different methods of doing that. This is a handheld smoke generator, and we can visualize the airflow patterns in the space. It's very, very helpful to see where is the airflow going. And so the airflow patterns matter because you may not be downwind or in the corona of corona, but once you start adding the HVAC, and let's say you have a supply diffuser here and your exhaust is over here, even though our infected person is breathing away from the healthy person, when we look at the airflow patterns, all of a sudden, those materials are going to start circulating back towards that healthy person. And that's where the exposure is going to occur. So we want to understand what are the airflow patterns in the space. So we took that a little bit step further. We've been using mannequins in our testing of laboratories for decades, over 25 years. And we use mannequins to simulate a person in that environment so that we can have an idea of their impact on the airflow patterns. And in this case, we are equipped, each mannequin, with the ability to exhale a small particulate, in this case, a fog that we could help visualize. So we see, as we're looking at the airflow patterns in the space, we can see that it is moving towards and across a room. There's a lot of stratification here. So how well mixed is this space? And if we take a look at another video here, we have this person here is now the one that's exhaling. They've got a mask on that dampened down the projection. But as we begin to see the airflow patterns here, they're being released. And because of the airflow patterns in the room, they're moving them, right to his buddy over here, who's going to be inhaling the effluent from this person. If that person's infected, there's a high likelihood that this other person here may be exposed and also subsequently become infected or ill. So we have to look at the airflow patterns with space, and assumptions of a well-mixed environment have to be challenged because the concentrations near the source may be dramatically higher than what you get in a well-mixed scenario. So we take this information, we start looking at, well, what can we do about it? Now, if I was in a counter-serve type of business, maybe it's a pharmacy or perhaps it's an auto parts store or a lunch counter, whatever it might be, I'm a healthy person. I'm working in that space, but I've got visitors coming in. I can't control necessarily who walks through the door, but I anticipate someone might be infected depending on the rates in the area. So if I add my HVAC and I notice that I've got a supply diffuser over here and exhaust behind this person, guess what? Where are the airborne materials going to go as they begin mixing with the air? They're going to spread throughout the space, ensuring everyone gets exposed. Now we could take the same concept and just flip the air supply and the exhaust. Now this person's standing in the clean air that's helping to sweep it back towards the exhaust. And so we're providing a little bit of isolation by having the airflow work to our advantage of helping move the materials where we would like them to go. And that's the way labs are designed, to go from low hazard to high hazard. You walk in the door, you want to be in a low hazard area. As you move towards the back of the lab, you go to the higher hazard areas. And so this concept can be looked at for the design and operation or renovation of spaces. A waiting area, where you have people come in. When I took the children to the doctor, they'd say, oh, sit over here. And then I'd look at the ceiling diffusers and be like, it doesn't matter where you sit in this space, you're likely to be exposed. So how do we take and manage the airflow so that it's creating these areas of isolation and helping to mitigate the risk of exposure within these spaces? It's possible, and the tools exist to do this, but we have to be able to implement them. Now, the last part of it is the tracer test. So we've done some visualization, still qualitative. It looks good, but does it really work? And how would we challenge it? So we can add a little bit more sophistication. We've got methods to generate an aerosol tracer, right? So we can generate it. We can look at gas concentrations, particulate concentrations, and look at the spread throughout the space. And this allows us to look at dispersion, accumulation, and decay under a whole variety of different operating scenarios. So in this case, we tested the room at different conditions with and without the implementation of air purifiers. These air purifiers are just on the floor here. And so they're generating clean air into the space and using the filtered air. But how effective are they? And where do we locate them? So in this case, we locate them to create some cross airflow patterns, putting the clean room down, the clean air back into the area where the occupants may be sitting. Well, looking at the data, with the filters off, we found that in comparison, the actual data to the theoretical data, what would happen under a well-mixed condition, the actual concentrations were 3.5 times greater than what we anticipated at 4.5 air changes per hour. That's pretty discouraging. We thought we had a lot of air, but it turns out because of the airflow patterns and the accumulation within the space, it was suboptimal. So when we turned the filters on, it had an impact of mixing the air up a little bit, but it was still 2 times worse than theoretically well mixed. But that reduced the concentration by 42%. So just turning the filters on was a significant reduction in the potential for exposure, and that's a positive in my mind. We don't know how low we have to go. We also were generating particulates in that space, and when we looked at with and without the filters, we saw a 39% reduction in dose. So the dose is the accumulation plus the dilution. It's the entire period of time for the exposure to occur. And so when we need to look at is the dose and how do we minimize that dose? The backside of the curve, the decay is important, but so is the accumulation part of it. We need to know how much and how long do people get exposed. So by looking at this kind of risk-based approach, we know we need a multifaceted program that has administrative controls and use of masks and other types of techniques. But where do we apply them? In the lowest level of risk, maybe it's a vacant space. I'm not concerned about that. I'm not going to spend any resources on that space. But as I move towards the level 3 and level 4 spaces, that's where I'm really going to pay attention. That's where it's necessary to make the investment to make better spaces better. And so by knowing where these spaces are, we can apply more or better techniques. And that culminates in an airflow management plan. The information you're collecting, the floor plans, the information about the HVAC configuration, how much air flows through the building, that's really good information, not just for COVID, but for long-term operation. This may not be the last pandemic, but there's also things like seasonal flu, and other issues. And then there's other indoor air quality issues that come into play. And the benefits of having this program can't be understated. By gathering this information, it's not only helpful today, but it's helpful for the future. And so here's some information that you would collect. How is the space being utilized? How does the systems operate? What is the testing and maintenance procedures? And how do you manage change? Because if you change the application of the space, you may have to change some of the operational parameters. So these are parts of the overall program. So I'll finish by saying that we can evaluate the risk of exposure and the potential for transmission. There's a lot of really cool tools out there to do so. We can evaluate and target spaces based on this risk, and not all spaces are going to require special measures. We can apply modeling to help us evaluate ventilation effectiveness. We can apply tests to evaluate accumulation and dilution. And so we have tools that can be utilized to help reduce the risk of exposure and create safer environments. The airflow management program is a must. In the United States, and part of the American National Standard for Lab Ventilation, it requires all facilities to have a management program because we know the importance of HVAC on the health of the building occupants. And then finally, coordinate, communicate, and train the key stakeholders to understand the importance of these systems and how impactful they can be on achieving better outcomes for all. So through this process, plan, assess, optimize, and manage, we can dramatically reduce that risk. Okay, so that brings me to the end, and I'm glad to answer any questions that may have come in.
Okay, thank you so much, Tom. You know, with the sort of sake of time, because we want Dr. Sigur to have enough space as well, I thought we just might share one question with you at the moment, and then maybe we can address any other questions after.
Sure.
And the comments are coming through about what a great job, how good the presentation is, and fabulous visuals. So just thought I'd let you know that. And also just to share with everyone else, Tom actually shared a tool with OCAO that we circulated to our occupational hygienists, just to kind of prioritize where to increase the ventilation in the rooms. And it's a pretty useful tool, actually. And I'd sort of recommend anyone else to reach out to Tom and ask for a copy of the same tool and give him feedback on what they think as well. So the question is actually from Maria Negulescu. Hi, Maria. Good to see you again. Tom, this is a great info. Would you have some recommendations for some good portable air filters? How should they be sized?
So, you know, okay, so about portable air filters, there's all kinds of systems that are now being developed, but filters have been used for, you know, 100 years to protect people. They're a tried and true measure. You can filter out contaminants, but how much airflow you need to move through the unit and how it moves through the room is a function of a variety of different factors. You need to know the size and configuration of the room, so the room volume, and then you can use calculations for the clean air delivery rate to help you determine the appropriate amount. So if you want 2 air changes per hour in a space of a particular size, you can calculate how much flow would be required, and then that would allow you to determine the size of the air filter system. Now, you go to other types of systems, bipolar ionization type of systems and so forth. Those have a far different set of criteria for what would be appropriate for a space. So I'm going to leave that question really to Dr. Siegel because he's the expert on filters. So I don't want to get into an area that clearly we have a resource here that is a true expert on that issue.
Okay. Thanks, Tom. And I think we will leave that to question till after Jeffrey speaks. Also, he'll add to that. I just sort of thought it might be worthwhile quickly just touching on this question because it just came in the chat box. And it's around well mixed air. It's got well mixed air as the usual objective, but you note its shortcomings. Could you please comment on strategies for displacement ventilation? Is that an easy answer that, you know, or is that something we could probably leave to the end as well?
So we wanted a well mixed or better, right? So if we're trying to dilute and remove materials, if you have a well mixed space, you're using the volume of the space to help with dilution. And that means you've got to spread the contaminants out throughout the whole space. And where we're trying to minimize the spread, a well mixed or a compromised space where there's zones of stagnation or what we call dead zones, those can allow for accumulation. So we want a well mixed or better. All of the calculations, Wells-Riley and other standards are based on well mixed. But as we start looking at the use of displacement, that's where we'd look at in a laboratory. We'd want the airflow to help sweep the contaminants out. We want to use the airflow and the airflow as the ability to move the materials in the direction that we would want to dilute and remove them. So displacement is sometimes has a connotation from floor to ceiling. We look at it from ceiling to floor or from across the room, transitioning across the room. There's various ways to do it, but we have to look at where do we want to move the air. And we certainly don't want to be the one that's downwind of all the contaminants. If you're near the exhaust, you're likely to get the highest dose. So we have to be very careful about it. In most spaces, well mixed is the objective. And if we can improve it beyond that, that would be great. But very, very few spaces in our experience are truly well mixed from that philosophy. So we have to really be careful about how we apply some of these tools and techniques.
Great, thank you very much. And yeah, I just a check just came in. Low velocity displacement ventilation should be far better than a dilution system. Just came in from William Ross to everyone. So I might just sort of stop it there and just say thank you very much. And it's great if you can stay on to the end. We really appreciate your time again. So thank
Absolutely.
you.
My pleasure, Kevin. Thank you very much for the opportunity.
Great. And I'll now hand it over to Jeffrey Siegel. Over to you, Jeff.
What I want to do today is talk a little bit about filtration and ventilation as solutions for COVID-19, or how to reduce the risk with filtration and ventilation. And I want to, towards the end of the presentation, have a specific occupational focus to some of the comments. So first, we've all seen lots of figures like this one before, but I want to make a very big picture point here. And that point is there are different ways that this virus can be transmitted between an infected and an uninfected individual. There's been a lot of discussion of close contact. There's also been, throughout this afternoon and more broadly, a discussion of longer range airborne transport. And then there are some other indirect routes, one of which I'll make some comments about a little bit later. But the reason I wanted to show this is we're really dealing with a multifaceted problem here, and we should consequently take a multifaceted solution. And so even though I'm going to be making the case for filtration and ventilation, I want to say something that Kevin said at the very beginning, and it is really important. There's no silver bullets here. All there is risk reduction approaches, and that Swiss cheese approach where you're trying to have many layers so that the holes don't line up is really, really critical. But even though I'm going to be making the case for filtration and ventilation, I don't want anyone to come away from this thinking that they're magic, that they deal with the risk. They are layers of supplemental risk reduction. They can be very important in some environments, some of those higher risk environments that Tom was talking about, but they're certainly not a replacement for things like masks, physical distancing, and I'll talk a little bit about surface cleaning and so on. The other comment I want to make about filtration and ventilation is that it's insufficient to just have a filter or to have ventilation. You have to do them well. And so a lot of this talk today is going to be about what do I mean by that? What do I mean to do them well? So first I want to make the case. And I could make a long, complicated case about filtration and its ability to remove viruses, but I'm going to make a very simple case. If you look in the literature, there are several papers in the literature, including those that are shown here, where respiratory viruses, both DNA and RNA viruses, have been recovered from filters in buildings. So if the filter can remove a virus, we know that because we're finding the virus there. And maybe just focus on the bottom paper here for a second. This was in a hospital in Oregon where there was a small number of COVID positive patients, and they found the virus on both the pre-filters, which are a little bit lower efficiency, although still reasonable filters, and the final filters, which were very high efficiency filters. And so we know that, the RNA, at least, that doesn't mean the infectious virus, but at least the signature that the RNA, that the virus was present, can be found on filters. So, filters can remove the virus. There's also been a lot of research on ventilation. This is, I think, the strongest paper. This was a systematic review by Hugo Lee and his colleagues almost 15 years ago. This is obviously before COVID-19, but it included data from SARS-1. And basically what they found by looking through about 40 papers in the literature that measure disease transmission rates and ventilation rate is that there is, strong and sufficient evidence that shows that ventilation and air movement can lead to the transmission of these, or there is an association between ventilation and the transmission of these diseases. And so we know that low ventilation is bad. The other part I want to mention about this article is that we don't know enough to say what the minimum ventilation rates are for safety. And so right now, all we know is the more ventilation with outdoor air, the better. The other comment I'll make, because it came up in the discussion earlier today a little bit, is that I encourage people to look at an Ashrae standard, for example, Ashrae standard 62.1, which is the commercial ventilation standard. And if you look at the main table that tells you what ventilation rate you need for different environments, there's a little footnote in that table. It's footnote B. And that footnote says that, the numbers in the table that Ashrae says you need to provide for ventilation are not intended to provide protection against infectious disease. They're meant to provide acceptable air quality. And so that's important because right now we can't say how much ventilation you need. We can just say we know that ventilation is good, and the more ventilation, the better. So now let's go back to filters and talk about how we make them work well. And there's kind of three pieces to making filters work well. The first thing is you have to get whatever you're trying to remove to the filter. The second thing is that filter or whatever air cleaning device you're using has to remove the virus from the air. And then the third thing is the filter has to contribute substantially to removal in the room. And if it doesn't contribute substantially, if there are other loss processes, for example, ventilation, then the filter might not offer as much benefit. So just to give you one piece of how this gets complicated, that's the figure on the right. This is what's called the runtime, or the fraction of time that the fan operates in residences. These are about 6,000 homes with residential central forced air systems. And so that runtime is how often the fan runs. And on the bottom axis, there is the outdoor temperature. And what you see here is a huge amount of furnaces come on more when it's cold, but there's a lot of scatter, and the important thing is the red dashed line there that's at about 18%. That means that in the typical home, a central forced air system doesn't operate for 80+% of the time on average. That means you can have the best filter in the world and air isn't going through it most of the time. And so this is kind of the first piece of the puzzle. You really have to think about the airflow piece if you're trying to use any type of filter. The second thing is around efficiency. So this is data from a study of 20 Toronto homes, all with the same relatively high quality MERV 14 filter. And what we did is we put the filter in place and we measured its efficiency as a function of particle size. And every different symbol and fill here is a different home in the study. And you can barely see it, but there's a black line in the upper right part of the picture. That's what the filter was supposed to perform at, according to a standardized test, the Ashrae standard 52.2 test. And you can see, and the reason I wanted to show this picture, that in many of the homes, the filter is performing worse than we might expect it to perform because of its MERV rating or its efficiency. And in some homes, it's working much, much less than we might expect. And so there's a lot of reasons why this happens, but one of the big reasons is something called bypass. This is a commercial building in Montreal, and you can see that there are both big gaps where the filter is kind of pulling out of the rack and smaller gaps where the filter fits into the rack. And of course, air preferentially goes through those gaps. So one of the big things about using filters well is that you have to make sure that the air is actually going through the filter and not going around the filter. And it's surprising how common of a problem that is. Using ventilation well has a different set of challenges. So very often there's a capacity challenge. You would like to ventilate more, but it's hot outside, or even more commonly, it's cold outside, or even more commonly, it's hot and humid outside. And you just don't have enough heating or cooling to handle additional ventilation. And so there's a bunch of solutions you can use here. You can limit the ventilation when you don't have the capacity. You can provide additional cooling, or in rare cases, maybe heating, to allow for an increased ventilation. There's another concern around humidity. And the first issue is that when humidity is low, so you can imagine a cold winter day in much of Canada, it's relatively dry outside. And so the more you ventilate, the drier it gets inside. And when it's dry inside, those little respiratory droplets that contain the virus, the water evaporates from them and they become smaller, and they can remain airborne for a longer period of time and potentially drive infection. There's other problems. We become more susceptible to most respiratory diseases when our mucous membranes are dry because the air around us is dry. And then there are comfort concerns as well. When obviously if things get dry or too humid, we don't feel comfortable. So, there are solutions here too. You can add supplementary either humidification or dehumidification depending on the season. I'm going to make some more comments about humidification in a second. It has to be done carefully to work. And then, of course, ventilation, what you're doing is diluting indoor air with outdoor air. And if outdoor air quality is poor, you are trading indoor risks for outdoor risks. Now, for COVID, it's very clear. The source is inside, and we want to get rid of it. But the challenge is there are other things outside. So you can imagine an environment that has poor outdoor air quality, as some urban centers do. You can imagine a building that's near a roadway or some other source outdoors. And so we really have to think about ventilation much more broadly than just in kind of a single issue like COVID sense. Now, I want to talk about humidity because there's a lot of interesting issues around humidity. It seems like an obvious thing to do is in the dry winter, humidify. That's what many of us do. The problem is humidity comes with harms too, or humidification comes with harms too. So we've known for over 30 years, as the article that I've put in the upper right there says, that if you use ultrasonic, or what are often called cool mist humidifiers, you're going to get a ton of particles in the space. And those particles come predominantly from minerals in the water that end up as small particles with potentially quite serious health effects. So perhaps because of that, some people use evaporative humidifiers instead. That's what, for example, I have in the central system in my house. But if you look at the data, evaporative humidifiers are often not very effective. They don't actually raise the humidity that much. And the real solution here is something called steam humidifiers. They're much more expensive, and they've got scald risks, and they have to be maintained well. But if you really want to change humidity, that's the way to do it. And any humidifier is going to need maintenance. Ideally, you should use distilled water. And, remember that we have other risks beside COVID, and moisture problems are a very serious risk, especially for children in buildings. So you can't just humidify without managing that risk as well. And just as one demonstration of this, we did a study not related to this, but happened to come across it in where we measured the particle concentrations for a year in 20 Toronto homes. And this is one of our sites. The red line is the median concentration over the entire year in this home. And it had the highest concentration of any of the homes in our study. And we had no idea why. And you can see that every day it went through the same pattern. They were starting at about midnight. There would be this big increase in particle concentration, very, very high levels, much, much higher than anywhere else. And then it would start decaying after about 3 hours or so. And make a long story short, it turns out it was this little ultrasonic humidifier that it's an essential oil diffuser. You put some water in it, you put your favorite essential oil scent in it, and what you have is an enormous particle generator. And some of that is coming from the oil itself, but a lot of it is actually just coming from the water and the minerals in the water. And this thing is tiny in scale, and so you can understand that larger scale humidification can be a risk as well. Tom did a great job talking about airflow, but another thing I want to talk about with ventilation is that you really do have to think about the distribution. And, you know, people who think about airflow in buildings think about this a lot. I think this came into the public eye very much with this article from a restaurant in Guangzhou in China, where there was people sitting upstream relative to the flow created by a mini split air conditioner, and that spread the virus to people sitting at tables downstream. And so, you know, this issue of airflow is really important. And I don't have to talk a lot about it because you just heard a lot of great things about it. But I would point out is, you know, we don't have smoking gun here yet, but we are seeing in different places in the world some possibility of kind of inter-unit transfer in multifamily buildings, where air can go through something called the stack effect through open chaseways or open passageways between floors and buildings. These can sometimes be associated with plumbing. These can sometimes be associated with things like elevators. But you have this ability to move air between different spaces in a building and potentially the virus as well. So this is just one of about 5 or 6 articles in the literature. And this one is from an apartment in South Korea. And you can see that the red in the picture on the left shows that there was this spread of cases vertically in the building. And there was no reason to suspect social contact or even incidental contact in places like elevators that led to this. So we really do have to think about the air movement and the air flow on a room scale, but maybe on a bigger scale as well. So there was just a question about, air cleaners and how do you know what type of air cleaner you should use? And I hope we get back to that question in the Q&A. But I do want to take a moment here to talk about the fact that there is this proliferation of air cleaning technologies. And for the record, these air cleaning technologies have been around for as long as I've been studying indoor air, and much, much longer than that, in fact. And the tricky thing here is they go by different names, and sometimes the manufacturers make up names and other things, but some of the common ones are photocatalytic oxidation, plasma ionization. And I can sum up everything about how I feel about these alternative technologies by saying, you know, you should really need to do your research. You really have to beware. And we've known this for a long time. The quote is from Dr. Pettenkofer, and he's a German chemist who was kind of the great-grandfather of the study of indoor air quality. And, you know, he makes the point a long time ago that, you know, we really have to be cautious here. And, you know, all these terms people use to describe air cleaning technologies, they don't really have formal scientific definitions. So there's a cluster of different technologies that are used in different ways. And in almost every case, there's not any independent evidence that they work. The manufacturers often provide lab reports and other things that suggest that they're effective. But if you actually dig into the details, there's often a lot of questions and a lot of concerns about whether they are. And I think even worse, some of these technologies cause harms or potential harms to the indoor environment. Ozone, which is a respiratory irritant and a chemical oxidant, is emitted by some of these technologies, as well as other byproducts. And some of these technologies generate ions, and there's been a couple of large recent studies that have shown that ion concentrations in indoor environments can be problematic for certain cardiovascular health outcomes. And so really buyer beware and really pay attention to the evidence. And right now we have technologies that work. We know ventilation works if it's done well. We know filtration works if it's done well. And we also know that ultraviolet light works if it's done well. And you know, there are 2 UV systems that we know can be effective. In-duct systems where the UV is in the duct, and something called upper room UV where the UV is installed near the ceiling. And there's a whole list, it could be a whole separate presentation of the things you need to do to make UV work in those configurations. Airflow management being the big one, because really you have to make sure that the air is spending enough time illuminated by the UV lamp to inactivate the microorganism. And there's, in that line, there's a lot of other UV systems, those that are designed to irradiate cooling coils and drain pans, or those in portable systems that don't have evidence of efficacy. So I want to make a point about UV lights. As I said, there's a whole list of things that you have to consider in doing them well. But the one point I want to focus on in this kind of sea of concerns or sea of things you have to pay attention to is relative humidity. This is a paper from about 15 years ago. And what you see here is, I forget even the microorganism that's in question here. But what you see there are lines of removal at different relative humidity rates. And the steeper the line, the more kill or the more inactivation of the microorganism you're getting. And you can see that the line is quite steep when you're at 20% relative humidity, and it's much less steep when you're at 90% relative humidity. And so if, you know, this just goes to show that even UV, which can work if it's done well, you have to think about the broader context and the environment in which you're using it. I want to finish by talking about a few occupational concerns and about something that hasn't been talked about today yet. And so, you know, throughout this pandemic, I've read lots and lots of papers, and, you know, we've had a lot of bad news this year, let's be honest. But this is the only time where I read something and I was like, oh, this is really a problem and we're not talking about it at all. So this is a paper that's quite complicated. It's quite a good paper. And the upshot of this paper is they looked at how, this is for flu, not for SARS-CoV-2, but they looked at how flu could be spread. And what they did through taking different guinea pigs, some who were infected with the flu, influenza A, and some who weren't, and looking at how they spread the disease. And to make a long story short, one of the things they found is that the main way that one guinea pig was spreading the disease to another guinea pig was through the virus on bedding that was resuspended in the air, because, you know, guinea pigs move around and cause stuff to get kicked up in the air. And why this gave me so much pause is infection was being spread. We've always known that virus, RNA, and DNA can be spread this way. But I had never seen it before where infection was being spread. And, you know, they went further than that. They showed that, you know, just by taking a tissue that had the influenza virus on it, they could just rub the tissue together and you could get aerosolized flu that was infectious. And so I think that this is really important, and it's unclear how important it is in all environments, but I think there's certainly a potential for concern in occupational environments. And even though there's been really a diminished focus on surface transmission, and that may be appropriate, I'm going to suggest that we might want to pay a little bit more attention to that in some environments. We know that environments where have high temperature or sunlight or low relative humidity are all good for reducing the infectivity of this virus, but viruses in general on surfaces, as well as, of course, just time. But we also know that, there's certain activities that can cause particles to resuspend and make those infective particles come off the surface. And another article earlier on in the pandemic that gave me a little bit of pause was some work from a hospital in Wuhan. And to date, the highest airborne concentration of SARS-CoV-2 that I have seen in any article in the literature is in the room where staff donned and doffed PPE in this hospital. And so you can imagine that the action of taking on and off PPE causes some of that virus to go in the air. Now, this article, and it turns out in general, it's quite hard to measure infectivity. So we don't know if this is actually an infective risk. Just because the virus is there, it doesn't mean it can cause the disease. And so, I'm not saying that this is the end of the world, but I'm saying from the precautionary principle, you really need to pay attention to this in some environments. And so to the extent you can don and doff PPE outdoors, especially in environments where there's infection, to the extent that you can treat environments as high risk where there is airflow near surfaces and other things, fans and so on, movement that might resuspend. And again, we don't know how big of a risk this is, but I think we're doing a little bit of a disservice, especially in some environments, by ignoring it altogether. So if I were to wrap up everything I just tried to say, make sure you're using a good filter, whether it's portable or central. Make sure lots of air goes through it, and change it frequently. Remember that the filter is capturing viral material, and it's unclear whether that represents an infectious risk, but treat it as it is until we know otherwise. Ventilate as much as you can, and paying attention to the negative possible harms. But don't use filtration and ventilation as your only approach. Watch out for any of the alternative technologies unless you have independent confirmation that they actually work and that they'll actually work in your space. And of course, pay extra attention to high-risk spaces, either because they're poorly ventilated, because people can't take the primary measures like masks, or because there is crowding, or any number of other risk factors. Finish there.
Thank you very much, Dr. Siegel. It's interesting, the last bit of information you shared. I remember seeing a video of healthcare workers in China, and they introduced airborne precautions towards the end of January, and they had very rigid requirements for personal protective equipment. And I remember seeing a shot of a PPE dedicated area where there was a buddy who was also in PPE, but they would help the person don and doff their equipment, but it was dedicated, that was sort of isolated in that particular area. So that's and just the fact that, we've really got to be careful of, re-entrainment of the virus from surfaces and getting airborne. I think that's a really important to think about as well. So just, and I'm just looking at the chat box at the moment, and I'm sure this is on everybody's mind, okay, we go out and buy an air purifier. It's going to make a difference if we have the right one and it's properly maintained and the filter works properly. It actually comes from Margaret, and she's asking us about, are there any Health Canada requirements? Is there any kind of accreditation process where like a respirator, you can actually see that it's either NIOSH approved? And is there anything that people can do as far as, figuring out which is the best one, so to speak?
I call it the Wild West. There is, to make specific health claims, there are laws and there is a process. Sometimes that's skirted around, but that issue aside, I think that the bigger issue is that you can make claims about efficiency, you can make claims about a whole bunch of different things. And as long as you're not making a health claim, you will not get any regulatory scrutiny. And it's really a problem because what a lot of manufacturers do is they make a claim that's technically true, but not relevant to real environments. So the most common one that I think we've all seen is you make an efficiency claim. And so our product has, 99.9% efficiency for the size of particles that contain SARS-CoV-2. You think, oh, that's fantastic. That's really high efficiency. That's great. But if no air is going through it, it doesn't matter. And there are, in fact, lots of air cleaners out there that have high efficiency and low airflow, and they don't make a difference in typical spaces. And I could go through a list of about 10 things like that. And so that's why the claims are so problematic, is that, the claim might be technically true. Sometimes it's not even technically true, but let's say we've got a claim that's technically true, but it's left in the hands of the consumer to evaluate that claim. And that's why we see school boards installing a lot of technologies that don't make a difference. We see, people like me, when I say things like I do, have manufacturers get up in arms and threaten legal stuff and all kinds of stuff like that. But it really is buyer beware. And so to make that more positive, here's what I think people should do. Look at independent sources, Consumer Reports, The Wirecutter, a variety of other sources. Do reviews of air purifiers. That should be a very good indication to you. The other thing I would say is that, we really, as a nation, we really have to work to have some government agency take ownership of this issue. And we really need good information provided to consumers. There's no scientific lab in the world that could keep up with the volume of devices that are out there. Not only that, it's a constant game of whack-a-mole. That is, a manufacturer makes a device, someone like me might test it if we have the research funds and capacity to do so, and then maybe the results aren't that good. The manufacturer makes a minor tweak in the device and says, oh, it's a completely different device. Your test is not valid anymore. And so we need high level to deal with that issue.
Okay, thank you. That is a concern. I mean, they talk about counterfeit respirators, but they're counterfeit because they don't, conform with a particular standard. So we haven't got the same kind of luxury with air purifiers by the sound of it. Val, did you have something to say?
Well, just there were a few more questions in the chat. I don't know if we have time, Jeff, if you can stay a little bit, or Tom, because I think these could be answered by either. It's about 5 to 3 right now. So maybe we could go just.
I can stay a few minutes after. Yeah.
Okay. Sorry, Kevin, though, I didn't want to interrupt. If you
go for it. Thanks.
Okay. So Laura Lee asked about opening windows, that it's often recommended as a way to improve ventilation, but they can also can open windows create turbulence and possibly spread contaminants. And what about mixing natural and mechanical ventilation? Are they challenging each other, kind of thing? Got anything, comments around that?
Tom, do you want to take that, and then I'll
Yeah, sure. So, well, my preliminary comment is the open window can be helpful. It depends on the outside air, the ambient conditions. And my preference, though, is to have an inlet and an outlet so that you are controlling the flow in the space, and allowing it to just naturally occur can, subject yourself to a lot of variation. And so getting something to create that motive force for the materials to move in a particular direction. And if you open up the window, if you happen to be downwind of that source, you might be getting a higher dose. So you really have to pay close attention to what the airflow patterns within the space are doing. Dr. Siegel?
Yeah, I would just, the only piece I would add to that is an open window is just a hole between the inside and outside. It's not a driving force, right? And so you're always going to increase ventilation, but how much varies a lot. And so I always say, of course, open a window if that's your only option, but I sure hope we can do better in general in our buildings.
Yeah. So then there was a comment from Dorothy about pointing out the limitations of Ashrae do you prefer their recommendations or those in the industrial ventilation manual for occupational hygienists, and why? One or the other, I guess.
That's a really hard question. It's a tough question, a good one. I would say that what I always tell people is I care less about the standards that you are using, because, you know, the building maybe was built 30 years ago when there was different Ashrae standards in place at the time of construction. So I care less about the standards that you're using and more about the approach to ventilation. I think so many buildings are, you know, the issue is not, you know, the absolute rate of ventilation, but how it's applied and how it's managed. And so I'd much rather people pick whatever standard they prefer and follow it and improve on it than getting into a debate about which set of standards is better.
Yeah, I would add to that and say I totally agree with what Dr. Siegel just said. But, you know, there's a lot of convergence on some of these different recommendations, and they're coming to similar conclusions. And much of the conclusion is that we have a lot more work to do. There's more work to be done by all of these organizations to address areas of their expertise. And I think that the failure to recognize aerosol transmission early has led to us playing a game of catch up, trying to get, you know, technologies and solutions that need to be further funded and have better research so that we can get tools and techniques that really make a difference.
Okay, thanks, Tom and Jeff. So another one about humidification and building envelope. I know there's skepticism about even 40% relative humidity in cold climates because of the risk of condensation, especially in older buildings. So I don't know if any.
Yeah, so the only comment I would make about humidification is I run into this issue a lot where there's kind of a little bit of a split in terms of building recommendations and medical recommendations or public health recommendations. And I think humidification is a good typification of that. And I really hope that, you know, one of the things comes out of this pandemic. I mean, we started this session with a doctor talking about ventilation. Now, in some ways that's heartening, but I sure wish that that doctor had been talking about ventilation, you know, a year and a half ago when it was still really important, you know. And so I feel like humidification is one of a set of issues that we should really be, I don't know the mechanism to do this, but we really need much better collaboration across disciplines.
Yeah, no, that's a really good point. Anyways, we could go on. That's another whole session, I guess, experts talking about things that aren't in their field, but it adds a dimension from their perspective or their lens, right? It's enriches the discussion as long as they're humble about it. So another question, which I think is a good one, about related to multi-unit residential buildings, can the spread through ventilation only go up?
Can I add to that too? Sorry, can I add to that too? Something that I've thought about, you know, in an airplane, you have the air coming down, and I've read some information that says that when you expel the virus, because you're breathing out hot air, it can go up. So I just thought as it relates to an airplane too, for example.
Yeah, no. So I think, I mean, all Tom talked about was air movement, and I think that's a huge issue. I think with multifamily residential, so there's a famous case, you can Google it, Amoy Gardens Building E in Hong Kong for SARS-1, where one index case spread to 200 other individuals in this apartment building. And that is, you know, it was through a bunch of confluence of weather factors and building factors. And I'm not saying that that is common and is going to happen everywhere, obviously. But I do think there is this important point that it can happen. And yes, it does tend to happen vertically, but it can happen sometimes. It's driven by temperature difference. So if it's hot outside and cooled inside, then the flow will be down. And if it's cold outside and hot inside, then the flow will generally be up. But there's a lot of other dynamics here. And the one other thing I want to say about that is, remember, it's not through the ventilation system. These are through passageways in the building that are there for some other purpose. So one of the building where there's an outbreak that's being investigated in Ontario, in every bathroom in the building, there is a panel access door to a plumbing chase that runs the height of the building. And so a hypothesis, and there's not evidence for this, is that the reason spread occurred in that building was because of airflow that went through this passageway that has plumbing pipes, both the sewer and the water pipes in them, from one unit to another through this mechanism. So again, I don't know how important it is. I don't know whether it's always important. There's real questions about whether the virus can even still be infective after it transfers a long distance through some pretty inhospitable environments. But I think it's something that I just wish that when there was an outbreak investigation, we would at least say, is this a possibility? Should we even go down the road? And if you look at the countries that are very proactive in outbreak investigations, that's exactly what they do. Mm-hmm. When there's an outbreak in an apartment building in Hong Kong, the people on the ground show up. Some of them have epidemiology expertise, some of them have public health expertise, some of them have building expertise, and they all investigate the factors and then come to a decision about, okay, what needs further investigation? And I sure wish we had the capacity to do that here.
Yeah, I think that retrospective contact tracing, I think comes up frequently, that we don't do anywhere near enough of that here.
Yep, absolutely.
To understand the transmission.
Yep.
There's a few comments around if surfaces matter, that the cleaning with soap and water can work most of the time, and also I think you talked about the device certification, and somebody put in the AHAM American system, but there is one here. Can you please discuss about CFD particle tracking technique for aerosol transmission, and what are the advantages and shortcomings? And is there enough information on COVID particles to show the reality?
So I don't do CFD in my research. I know many people who do. I think it's a very powerful tool if it's in the hands of someone who knows how to use it well. I think the challenge with CFD is that it's all based on the boundary conditions and how well you know the room and the space which you're trying to model. And so, the people who do CFD for a living and do it well, they know how to make the CFD model reflect the reality in the space. It's as much, I must say, it's an art, because that's not quite right, but it is definitely takes a bunch of expertise to do well. And so in general, CFD is a tool. I think it's a little bit of, depends how it's done, which I know isn't a very helpful answer. But I think in a lot of cases, I would rather say, let's solve the problem in the room. The worst that happens is we're solving a problem that's not such a big problem. We're improving the indoor air in the space. And, that's still a pretty good outcome. The best outcome is that we're also reducing disease transmission. So I always look at this as, would I rather spend the money modeling the space, or would I rather spend money solving the problem? And I almost always come down on, let's solve the problem.
Yeah.
And I think that's where, Tom Smith's tool's very useful, because it lets you kind of prioritize where you need to provide ventilation, go to the higher priority area, and then really home in and improve the ventilation there. So it's like a control. It's a control banding technique. So it's like it just puts the risks into bands and then figures out where you need to put your controls. So, thanks.
Right. Yeah. If you're going to spend $1, you'd rather spend it on the most high risk space.
Yeah.
Absolutely.
There's one other, I think two others, and then I think we'll have to stop the questions and give you back your Friday afternoon. We do appreciate you. There's a comment more around the principle of diluting by a factor of 100 based on an occupational exposure limit, or PEL, permissible exposure limit, in the States. And but we don't know one for SARS-CoV-2, and I think that actually answers itself in some ways, right? Is what level of dilution is safe?
We don't yet know. Yeah.
And it's changing, I guess, with the variant, right?
Yeah, the infectious dose of the new variant is lower, so we don't know.
Yeah. So you can't. Yeah, it's as gets to the Alera that Tom was talking about.
Yeah.
And then there's a question related to the paper about the peak PM2.5 count. when you're talking about water vapor, the source is water vapor, what is the risk associated with that as a source of PM2.5? Presumably it's water. Is it minerals or other particles?
It's all, so several studies have looked at that question exactly. It's minerals in the water that are the heart of these particles, and they come out as particles in the size range of about as small as about 0.1 microns up to about 1 or 2 microns. And I'm just really surprised at how big of an emission source it is. And in fact, many people, you tell people this depending on what their water supply is like, and they say, oh yeah, I always notice that white stuff on the counter around my humidifier, like where I was using the humidifier. And that's it. That's what it is. You're taking minerals out of the water and putting them into a form that people are breathing them in.
I guess that's a visualization of what the fomites might look like too, if they were visible.
Yeah, absolutely. Yeah. Maybe we need more of that. Maybe that's a good thing. Yeah.
Yeah, maybe. Okay. Thank you very much, Jeff and Kevin, for moderating. And thank you very much for everybody who's hung in there and attended. I just wanted to remind everybody that this is a series of webinars, and there's another one next week that are updates from a medical perspective. Which will be quite interesting with 3 presenters with different perspectives. And then in the week after, we're doing a whole session on elastomeric respirators and how we can, it's a sequel to the March 5th session, and providing guidance on use of elastomerics. And then on April 9th, we have the looking back and going forward session, and we're actually just this morning talking about planning another session for April 23rd. So there'll be more to come, and it's all on the link that's in the chat right now. So we'll see you next time, I guess, and we will post the video and the slides in the next few days, probably by Tuesday or Wednesday. They'll be on our website. So thanks everybody, and thanks again, Jeff. We appreciate you joining us twice already, and it's very it adds so much more to our ability to convey information and that people can use in their workplace and in their homes.
Yeah. Well, thanks very much for the opportunity. Really enjoyed it.
Yeah.
Take care.
Yeah. Thanks everybody. See you next week.